So a quadric surface is one of the three-dimensional surfaces that you've probably heard of, like a paraboloid or a saddle or an ellipsoid, and then a hyperboloid of one or two sheets. They're basically three-dimensional analogues of the conic sections: parabolas, hyperbolas, ellipses, and circles. So these are basically the three-dimensional equivalents of or analogues to those. So generally, a quadric surface is a three-dimensional figure defined by the quadratic equation in three variables. And one interesting thing is that these quadric surfaces, we're talking about them, they're surfaces in three dimensions, but quadric surfaces can actually generalize to higher dimensions, which would be quadratic polynomials with more than three variables. So they would still be degree 2, but we could add more variables to this and we would still end up with quadric surfaces, although they would be hard to picture because they would be in higher dimensions. Okay, so let's look at some examples and use our steps to try to visualize them, and then we'll generalize them a little bit at the end. So what about f of xy equals x squared plus y squared? So step 1, symmetries. This equation remains unchanged if x is replaced by minus x and y is replaced by minus y, right? That's going to be, you're going to get the same result. So what that means is that it's symmetric across the yz plane and the xz plane. Now in this case, there are no missing variables. If we replace this with z, then there are no missing variables. So what about level curves? If we set z to a constant, then we get a circle. So if we take c equals plus or minus 1 or 0. Oh, sorry. So if we take c equals 1, 4, and 9, then we'll have circles of radius 1, 2, and 3. And then these circles would be placed on the plane at z equals c. So what we would have is at 0, it's a circle of radius 0. When z equals 1, it's a circle of radius 1. When z equals 4, it's a circle of radius 2. And then when it's way up here at 9, it's a circle of radius 3. So notice that the circle is only increasing by radius 1, but that the space between them is increasing exponentially. So what about sections? If we set x equals 0, then we get the parabola z equals y squared. So this would be a parabola on the yz plane. So it would go up like this and up like this. And then if we set y equals 0, it's the same thing. We'd have z equals x squared, and we would have one that goes back like this and one that comes up like this. And this is called an elliptic paraboloid. So the method works very well. We can tell from drawing it that it's going to be a parabola in 3 dimensions, right? And in this case, it's actually a circle, not an ellipse. So you could also, this is also called a paraboloid of revolution because it's symmetric all the way around, rotationally around the z-axis. Okay. What about z equals minus y squared in xyz space? Okay, so are there any symmetries? Yes, the equation is unchanged if we replace y by minus y. Now, are there any missing variables? Yes, x is missing completely. So what does that mean? That means it's going to be a cylinder along the x-axis. And what that means is that if we set x to a constant, the sections with x constant have to be the same because x isn't changing the equation. So in this case, the sections are all parabolas opening downward in the yz plane. So they go down like this, and then there's another one here, another one here, and so on. And it doesn't matter what x is, every time it's going to be a parabola of this sort. So that's all we need. This is the surface. This is called a parabolic cylinder. And the important thing just to know here is that cylinder doesn't mean a can. It means that it is unchanging along one axis. So even though this is actually open, it's still called a cylinder because the slices of x don't change. Okay. What about f of xy equals x squared minus y squared? So does this have symmetries? Yes. Both x and y can be replaced by their inverses. It has all the variables because again, well, this is z. Okay. Now, what about the level curves here? Make z constant. Then the level curves are given by x squared minus y squared equals c. So let's try c equals 0, plus or minus 1, plus or minus 4. So if c is 0, then we have x squared minus y squared equals 0, or x squared equals y squared. That is just a pair of lines with y equals plus or minus x. So that is just two lines, one that has a slope positive 1 and one with a slope negative 1. Okay, that's when c equals 0. Now, when c equals 1, we have that x squared minus y squared equals 1, and that is a hyperbola that passes through plus 1 and minus 1. And then if we have x squared minus y squared equals minus 1, we have a hyperbola that passes through the y-axis at plus 1 and minus 1. So this is c equals 1, c equals minus 1. And then if we do a couple more, if we have that x squared minus y squared equals 4, then that passes through the x-axis at 2 and minus 2. And if we have minus 4, it goes through the y-axis. Now, if you don't know where this is going, then this is still awfully confusing. Let's see if we can do some more here. So these are values of z. So this is 1, this is 2, so these are above the z-axis. Then this is minus 1 and minus 2, so these are below the z-axis. So let's take the sections and see if we can get a better idea. So let's try y equals 0. Then we have x squared minus 0 equals z. That is just a parabola in the xz axis. So let's try to draw this now in 3 dimensions and see what we can do here. So this is x, y, and z. This is in the xz axis, this axis, and it is a parabola going upward. So it goes up this way, and it goes back that way, this way. And then if we make x equals 0, we have that minus y squared equals z. Now that's a parabola in the yz axis opening downward. So it's going along this one and down, and then on the other side, going down. So along this way, it's going up, and along this way, it's going down. So now if we try to draw our curves onto this framework, what do we have? This one is above 0. It's at 1. Right at 0, it's the two lines going this way. And then this one back here is going out this way. And then that was a terrible line. It should go this way. And then at 2, it's the same thing. It comes out this way. And at 2 here, it goes up that way. And then going down this way, at z equals negative 1, it's a hyperbola coming across like this, and then another one even lower. And same over here. Here's what this surface looks like in Grapher. So this is called a hyperbolic paraboloid. So consider how this one is different from the elliptic paraboloid. With the paraboloid, you can slice it in 3 directions. And when you sliced it along the xy plane, it made ellipses. And if you sliced it vertically, it made parabolas in 2 directions. Here, if you slice it horizontally, we get hyperbolas. But if you slice it vertically, we still get parabolas. So in both of them, in 2 directions, it's a parabola. And in the 3rd direction, it's either a hyperbola or an ellipse. And then, so the difference is that with this one, depending on which direction you slice it, the hyperbolae either go down or they go up. Whereas with the elliptic parabola, they go up in every direction. That's interesting. Okay. So some conic sections can degenerate into points or lines. Like an obvious example is if you had x squared plus y squared equals 0, that's basically a circle of radius 0. In other words, it's just a point. And the quadratic surfaces can degenerate in the same way into points or lines or planes. So let's just look at some of those. If we have x squared plus 3y squared plus z squared equals 0, then only 0, 0, 0 satisfies this equation. So it's a single point. if we have z squared equals 0, then the only thing that satisfies this is the single plane at z equals 0. So it's basically the xy plane is the only thing that satisfies that. If we had x squared plus y squared equals 0, then we have a line. This is interesting because here, if we're looking at it in 2 dimensions, this is a point. But here, because z is missing, that makes it a cylinder, right? So, but in this case, it's a cylinder of 0 diameter, so it's just a line through the z-axis. If we had x squared plus y squared plus z squared plus 1 equals 0, then, in other words, if you move the 1 over, it's x squared plus y squared plus z squared equals minus 1. So this has no points at all, because there's no points. No matter what, these are all going to be positive. You can't make this equal minus 1, so no points. And x squared minus y squared equals 0 is going to be 2 planes, one along the x equals y plane and one along the x equals minus y plane, or y equals minus x plane. So it's two planes like this. So when I say these are degenerate, we're only considering real numbers. I'll talk a little more about the complex numbers in a second. For instance, this one, it does actually have solutions in complex numbers. It would be a sphere with an imaginary radius. So that's not in R3. It's going to be entirely imaginary. That's why there's no points. Okay, next. What about x squared over 9 plus y squared over 16 plus z squared equals 1. Now, this one is different from our previous examples because, as I was mentioning a little while ago when we were looking at our techniques, this one is not a function of 2 variables. It's an implicit function because all 3 variables are here. So this is actually a polynomial x comma y comma z equals 1. So in this case, if we can, in an easy way, solve for one of these, we can do so, but in this case we can't because it would require a square root of any one of them and that would be a mess. So what we're going to do instead is just take cross sections in each direction and see what we get. So it's clearly symmetric over all 3 axes, same as the other ones. There's no missing variables. So now we'll take the cross sections in all directions. So if we let z be constant, then we get x squared over 9 plus y squared over 16 equals 1 minus c squared. So if c is between 1 and minus 1, then this is going to be an ellipse, right? Because this will be positive. So this will be an ellipse parallel to the xy plane. If the absolute value of c is greater than 1, then that's going to make this negative, which means, again, this would have to be imaginary because 2 squares cannot be negative. And then if c equals 1, then we just get the point 0, 0, 1, and if c equals negative 1, we get 0, 0, negative 1. So if we draw this, we have that if z equals 1, it's just a point there. If z equals negative 1, it's just a point there.
Cyclops there, Cyclops there.
And if it's between these two, then it's going to be an ellipse of some kind. So let's keep going. If we make, and we'll, to see which way it goes. So if we set x to a constant, then we get y squared over 16 plus z squared equals 1 minus x squared over 9, or c squared. So this is it's the same situation as here. This is c squared. This is also an ellipse. In this case, we have to have that the absolute value of x is less than or equal to 3, because then the 3 squared is 9, so then this would be 0. If x is plus or minus 3, then this is just a point. So if x is 3, then it's just a point. And then if it's anything between 3 and negative 3, it's going to be an ellipse of some kind going this way. And then same thing, if we make y equals c, we have that x squared over 9 plus z squared equals 1 minus y squared over 16. So in this case, we have to have the absolute value of y is less than or equal to 4. So if it's at 4, then it's going to be a point. Minus 4, it's going to be a point. So, whoops, my scale wasn't very good. So this is an ellipse that goes along around like this. And then in this direction, it's an ellipse that goes around like this, and it's an ellipse that goes around like this.
What's all this crap? I thought you said he was good at making bombs and robots and stuff.
So what it is basically, it's basically like a smushed football. If you think about a football,
What's he doing now?
is like an ellipse, but then with the stitches on top. But if you look at it from the end, it's circular from one end, right? So this is just squished, so it's actually elliptical in all three directions.
I'm not seeing it.
That is called an ellipsoid. What about x squared plus 4y squared minus z squared equals minus 4? Symmetrical in all three directions, nothing is missing. Again, this is an implicit function, so we'll take z equals c, and we have x squared plus 4y squared equals z squared minus 4. So this is very interesting because in the last one, we needed z to be within some kind of a range, but here we need z to be bigger than 4, because if z is less than 4, this is going to be negative, so this will be imaginary. Here, the absolute value of z has to be greater than or equal to 2. So if we try to graph this, if z equals 2, then it's just a point, and if it's minus 2, it's just a point. Then if it's bigger than that, this is going to be an ellipse, because then this will be, if z is bigger than 2, this will be a positive number. So this will just be an ellipse. So it's 0 here, but then as it gets up a little bit, it's an ellipse that goes this way. And then as it gets bigger, it's going to get bigger like this. And then same thing going down. 0 is just a point, but if it's below that, it's going to be an ellipse like this. And then if it's below that, it's going to be a bigger ellipse, and so on. That's interesting. So it's sort of the opposite of the ellipsoid in the last example, because there's nothing in the middle, and it only exists when it's getting farther from 0. Now, if we set y equals c, that's in the xz plane, and we have that x squared minus z squared equals minus 4, which is a hyperbola with the points at 0 plus or minus 2. So it's 0 and then plus 2, and it's a hyperbola in this plane. So it would go up from here this way, up from here this way, and then also minus 2. So it would starting here, it would go down this way and down that way. And if we make x equals c, then x squared is 0, so we have 4y squared minus z squared is minus 4. That's again a hyperbola. This time it's on the yz plane, but the points are still at 0 plus or minus 2. But here they're in this plane, so they're going up this way and down this way. So what do we have here? We have sort of a bowl this way and a bowl this way. This is called an elliptic hyperboloid, or a hyperboloid of two sheets. And in this case, it's a hyperbola in two directions, and it's an ellipse in the third direction. What about x squared plus y squared minus z squared equals 4? So this is almost the same thing, but here this is positive. What's that going to do? So again, there's symmetries everywhere. All the variables are there, and it's again an implicit function. So if we set z equals c, then we have x squared plus y squared equals 4 plus z squared, or changes to c. So this is interesting. So we have, at z equals 0, we have a circle with radius 2. And then as c goes up, the radius increases, right? So when z is 1, this is going to be 5, which is the square root of 5, just a little bit bigger, and so on. It's going to keep getting bigger as it goes. And likewise, if z is negative 1, it's still going to make this a little bit bigger, but it's going to be down below. Like that. And now if we try taking the cross sections, if we make x equals 0, we have y squared minus z squared equals 4, which again is a hyperbola, this time in the yz plane. And when z equals 0, then y is plus or minus 2. So it would be here and over here. And it's a hyperbola in this direction in the yz plane. And then it's almost the same thing for y equals 0, we have x squared minus z squared equals 4. It's exactly the same, except now it's out here, and they go up this way, down, and up this way, and down. So what's this make? It makes like a tube that is bent in the middle. This is called a hyperbolic hyperboloid, And again, because this is a circle, this is also called a hyperboloid of revolution. And one super interesting thing about these is that they are ruled, which means they consist of straight lines on this surface. Even though the surface is entirely curved, there is a line, a straight line that goes through here like this and all the way around. This one would probably come up like this, like that. So it's easy to make these. If you just have two circles and you put strings on them, between them, you can just twist them and you'll stretch it in, you'll squeeze it in and back out like that. Architects love to use this shape. And just to make sure we notice this, this isn't the only thing that's ruled. Any kind of a cylinder, for instance, is ruled as well, right? Because it's also consists of straight lines. Okay, one more. What about x squared plus y squared minus z squared equals 0? So I want to think about something here. When we have a hyperbola, so this would be x squared minus y squared equals 1, and it would go like this, right? And then if it's minus 1, it goes like this. And if we move the y over, we have x squared equals 1 plus y squared. Now, without the 1, if we just had x squared equals y squared, then these two numbers are growing exactly in alignment with one another. And this is equivalent to the lines y equals x and y equals minus x, which of course are these two lines. So the only thing that's keeping this from being the line is this little number 1 here. And the thing is, as the number grows, that number becomes less and less important. It becomes a smaller and smaller piece of this side of the equation until, at infinity, they would actually be equal because the 1 is totally irrelevant. So basically, what a hyperbola is, it has the slope of the asymptote, but it's just not quite there because of this little extra piece. But that piece isn't changing, so that as the numbers get bigger, you get closer and closer to that linear slope of the line. And then as you get closer to 0, it becomes more and more significant until when you get down to 0, then the only thing that matters is this one, and then you just have x squared equals 1. So given that, we had on the previous examples, we had that x squared plus y squared minus z squared equals 4 and equals minus 4. When it was positive 4, it made the hyperbola of one sheet, and then when it was minus 4, it made the 2 like this, with the gap in the middle. So what do you think this is going to be? If this is the hyperbola of one sheet, that's the hyperbola of two sheets. If it equals 0, it's just going to be down the middle. And that's what it is. This equation makes a cone, a double cone that meets in the middle. So basically, all of these hyperbola are trying to be cones, but there's just this little piece that's keeping them from quite getting there. And the closer to infinity you go, the closer to the straight line they become. So this surface is a cone. So just a couple more final comments about them, and then we will start on differentiation. There are actually 17 different surfaces possible from the general quadratic polynomial with 3 variables, but 8 of them are not true quadrics. Those are the ones that we looked at that are degenerate in some way. So the other 8 are, there's an imaginary ellipsoid, which has no real point. For example, x squared plus y squared plus z squared equals minus 1, because it has an imaginary radius. That's something that's interesting to think about. If the radius of a circle is I, then what does that look like? Something to consider. There's an imaginary cylinder with, again, no real points, which is the same thing, but it would be a circle with an imaginary radius. It has no real points. An imaginary cone with 1 real point. And then there are 5 reducible quadrics that decompose into 2 planes. And then it depends on how they decompose. They can be distinct or not, meaning that they're like z equals 0, it's 2 planes laying on top of each other. Parallel or not, and real or complex. So for instance, x squared equals 1 makes two planes, the one at x equals 1 and the one at x equals minus 1. But if we have x squared equals minus 1, then it's x equals I and x equals minus I. So they're still parallel planes, but they're complex conjugates. And then what we're left with is the 9 that we've gone over. There's the hyperbolic hyperboloid, the elliptic hyperboloid, the hyperbolic paraboloid, the elliptic paraboloid, and the ellipsoid. So one interesting thing to see about these is, if you look, you can kind of see the differences here. Like, these both have an ellipsoid in them, combined with the minus to make it a hyperboloid, right? And then whether it's one sheet or two sheets depends on whether it's a minus one or a plus one. The paraboloid the hyperbolic paraboloid has a hyperbola here, and then these are squared plus one variable of first degree. And then here, there's also one variable of first degree. So this is also going to be a paraboloid, but then here it's an ellipse rather than a hyperbola because it's a plus or a minus. And then the ellipsoid is everything plus. So there's nothing hyperbolic here because there's no minuses. Interesting. And then finally, these are 5. And then there's 4 more shapes that are called degenerate, which are the elliptic cone, the elliptic cylinder, the parabolic cylinder, and the hyperbolic cylinder. So the last thing to point out is that everything we've been talking about has been aligned along one of the axes, but they don't have to be. These different quadric surfaces can also be rotated in one way or another, and that's what, in the general polynomial, that's what the xy, xz, and yz terms are. So for instance, we know this is true because the most typical example is that xy equals 1 gives you a hyperbola like that. So it's still a hyperbola, but it's been rotated 45 degrees. That's what the xy term does. So the same thing can happen with these quadric surfaces. You can rotate them in any direction using xy, xz, and yz, but the point here is that they can just be rotated and translated into one of these standard forms. So these quadric surfaces are just very simple surfaces that are embedded into three-dimensional space. So they're good to work with when we're learning multivariable calculus. But just remember that these aren't the only surfaces in three-dimensional space. So for instance, there's what I call a field of bumps, which is sine x squared, or sine squared x plus cosine squared y equals z. And the implicit equation of a torus is where the big R is the radius of the outside of the torus, and then the small r is the radius of the tube. And notice, by the way, if you remember last week when we were talking about elliptic curves, one of the equations that we came up with, which was the equation to find one of the periods, was this. So they're not the same, but for me, they're similar enough that you can, at least I think, be convinced there's a reason why we keep talking about toruses when we're talking about elliptic curves. This is an elliptic equation. Here's the equation of a torus. There's something similar about them.
One last example just to show you can come up with all sorts of crazy surfaces. This makes one of these. The technical term for this surface is two-bump mountain.
So all these surfaces are cool, but in multivariable calculus, we're probably going to be looking at these quadric surfaces more just because they're relatively simple and still very interesting. Thank you.
Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.